Hey everyone, just wanted to do this last lecture video for the semester. This is on chapter 16, climate change. I'm going to rely on the textbook for a good part of this. I'm just going to kind of talk about the highlights and kind of more of the real world and practical fill in the blanks as you go kind of stuff. I'm going to rely on the textbook for most of the science and um, looking at the atmosphere and all that stuff. Um, what I'm going to talk about more tonight is the practical implications for climate change and what we could possibly do about it. I'll go through these slides. I'll mention some things. One thing that I wanted to point out is some of these photos in the textbook are really telling about the the reality of climate change. If we go back in our lesson, I can't remember what chapter it was. It was on the Easter Island, the creeping normalcy question that I gave you about people just get used to things and it's kind of the norm for them. Well, most of your lives that you've been here and been paying attention, hopefully, to the things that surround you, you've heard about climate change. And it might be easy to kind of like say, well, I'm not really seeing any big major implications of this, so is it really that big of a deal? Yeah, it is a big deal. Um, and you have to have kind of a big picture perspective about things like this to really grasp what's going on. And I think that's something that's very lacking in today's world is people being able to step back and say, hey, this might not affect me tomorrow, but it might affect my children in 20, 30, 40 years, or it might affect my grandchildren in 100 years, or whatever the case. So, so this is one of those things, if we start talking about geologic time versus human time, this is pretty remarkable, the change that we're undergoing right now in our atmosphere with regards to climate change. This is nothing that's even been seen on record in the geologic history. The records that we can produce from some of the things we're going to talk about later in this presentation, we've never seen anything like it this fast. The rate at which the Earth is warming, the amount of CO2 in the atmosphere and other greenhouse gases is just alarming how fast it's happening, and it's even exceeding what scientists thought it would, what a lot of the models thought would happen even from 20 years ago. I'm older than probably most of you that are taking this class, so I've been hearing about this for much longer than you have, and I remember studying this when I was in college. And, it wasn't a good outlook then, and it's only gotten worse since then. And we see the effects of this every day around our planet. However, going back to what I just said, people live in their own realities. They live in their own little space. They see their corner of the world. And unless there's some devastation happening in your backyard, you're going to think, well, it's not that big of a deal until it happens, until it's too late. And that's the problem with something like climate change. That creeping normalcy idea that we talked about way back early in the semester, this has a big effect on climate change. And of course, you have the other side of that where you have people that intentionally shoot these kind of ideals down. I've mentioned this throughout our class this semester. When we get into the real world politics and economics of the world, it's to their advantage to make this go away because they're making money on this, or they're afraid that their stream of money might be less if climate change is really happening and people want to do something about it. So that's one of the biggest hurdles that we have in something like this. You've got those two factors kind of pulling people in a certain direction, and for those people that like to think that people are trying to trick them all the time or buy into those conspiracy theories again, it's very easy to sit back and nitpick this and say, well, this is happening, well, that's happening. Well, what I'm trying to get you to do is I'm not trying to force you to believe any certain way. I'm trying to let you have the ability, and I think all educators would tell you this as you're in school. I want you to have the ability and the intelligence to be able to find the truth, to be able to research something and say, okay, I might not believe this, but I'm gonna go look this up and figure it out. That's what I want you to have the ability to do. Um, I hear a lot of people a lot of times say they don't believe in climate change. Well, this is not Santa Claus. It doesn't matter if somebody believes in climate change or not. It's scientific fact that it's happening beyond a reasonable doubt. There's no doubt that this is happening. So I just wanted to get that out there because we're going to talk about some of those things as we go through this lecture. And it's very important for you to grasp that understanding of how big of a scale we're talking about here. A lot of this is based on geologic time, and this photo is a very good example. This is of a glacier in Greenland, and you can see how it's receded over the past, what is that, 150 or so years, 170 years probably. So what you see happening is it's first of all, a glacier is an extension of an ice sheet. And think about it going down a valley like a river, and it's flowing toward some other area where it's melting on the end, like an ocean or a big lake or whatever is down here. So down here it starts to melt. So it's actually moving. Even though it's ice, it's being pushed off of this ice sheet and pushed down this valley. So it slowly moves over time. Well, now you hear about glaciers retreating. That means they're disappearing up the channels that they used to flow out toward the sea. So this would be the end of it. Well, as you see here, it's retreating over time. And when we hit the year 2000, that retreat became exponential. It's 10 times, returning faster, 10 times more now than it was prior to the year 2000. So if you compare the distance between here, basically 2001 up to 1851, that whole time it retreated this much. It's almost retreated that much since 2000, and this stops in 2015, so it's probably farther back now than it actually shows here. Again, another picture of something like this from 1941 to 2005. What is that, 64 years or so? And this is a picture of the same glacier in Alaska, the Muir Glacier, taken at the same time of the year. That is a tremendous difference in such a short amount of time in the two pictures. It was barren, just ice and land here. Now you see it's green. And that is twofold. One is it's warm enough for this ice to melt and retreat back up into the higher elevations, but it also exposes a lot more water and land, and with this vegetation, they're darker colors and they absorb more heat from the sun. So not only is the ice going away, but you're also creating more surface heat because of the absorption from the sun. So you can see how this starts to kind of snowball, pardon the pun, as we go forward. The more it opens up, the warmer it gets, and it keeps going and going and going. Now, the average global temperatures, and again, we're going to talk about how we can determine this. Of course, this graphic here is just since we've been able to record it on a human scale. But we have other ways to see this going back some other ways, like tree rings or ice cores from the polar regions. We can see how the climate was back in those time periods. But this is just from human recording of temperatures. And you can see the temperature has steadily increased pretty much since the year about 1910. It's gone up, 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 up. So that is directly correlated with the burning of fossil fuels. And you can see this chart. Again, if you look at our use of the raw materials that we use for different purposes, what we're putting into the atmosphere, you can see here carbon dioxide, methane, nitrous oxide. You can see all those things back year 0 up to the year 2000 and a little bit further. So they were pretty much flatlined across here until we get to about 1900 or so, and then they're just pegging off the charts. They're just wildly going straight up. And this has everything to do with population increase and our use of these natural resources, what we're doing, how we're burning them, and how much we're burning them. This is no coincidence. This is This is documented science. We can physically measure these things. So, just a little background. The Earth's climate, of course, we have the sun that sends heat and light and other forms of radiation to the Earth. There's always been a greenhouse effect here on Earth. Just the types of chemicals that we have in our environment. We've always had carbon dioxide. We've always had nitrogen. We've always had oxygen, as at least for the better part of Earth's history and what we're talking about here. Those have always been here. But remember, it's that balance that we need to keep things at that natural normal. And what we're doing right now is we're upending that balance. We're throwing a monkey wrench into that balance. And over history, if you look back, and we're going to see some of these in a minute, you're going to see these charts and graphs that show over different periods of heating and cooling in Earth's history. You're going to see different concentrations of these gases. We can tell that, again, by those core samples from ice is the best way to tell that. And it tells a story that once you get to a certain level, it's all going to crash down. It's all going to change. And it could be changed relatively rapidly. Again, we're talking about geologic history, not just human years, but geologic history. And even though that's a natural cycle, and yes, you're going to hear that gaslighting that I mentioned in the previous chapter, that people are going to say, well, it's always happened, so this is just natural. Well, there's a shred of truth of that. It is a natural cycle. It has happened in the past. But we're definitely, there's beyond a reasonable doubt, we're contributing to this accelerated heating right now. We've never seen anything like the speed at which we're heating this planet right now. That's not natural. That's not a natural process that we've seen before. And the other thing is to think about even these naysayers that say, well, it's a natural cycle. Okay, fine. So what if it is a natural cycle and we're contributing a little to it? Do you still want our society to collapse? Wouldn't it be prudent to at least try to do a little bit of something about it if we could put it off for a little bit longer? I mean, it's kind of a ridiculous argument, but it's out there because people want it to be out there. So we have these greenhouse gases that have always been here since life's been on this planet, but they're in balance. And when things knock them out of balance, then they have to reset. And sometimes that reset is what makes life difficult on this planet. We have glacial periods, we have extreme heat periods, and that's one thing that kind of contributes to the climate. Another thing, as far as the temperature goes, is variations in the Earth's orbit. So sometimes, and we're going to see some diagrams coming up on the next slides, the Earth is an elliptical orbit, and on top of that, so sometimes we're closer to the sun than others. We also have an axis that we spin on that sometimes wobbles a little bit. So sometimes it's a little bit more, the angle's a little bit more on it than it is other times. All those things together can kind of come together, and if they all line up just perfectly, they can slightly affect the climate and the temperature on Earth. And that's why some climatologists or paleoclimatologists believe that we might have had some glacial periods in the past. However, it has to line up just right, and we're not in one of those cycles right now. What we're doing right now is outside of that norm. And you can see here, this graph here is showing the temperature versus solar activity. And since 1880, we had a little bump here around the 1950s, but overall we've been pretty constant on our solar activity, yet our temperature has steadily risen. So we cannot contribute this to solar cycles or those type orbital issues only. This graph, and again this is in your textbook, this is just showing you the amount of radiation that comes in from the sun. It hits the Earth, and what these represent out here is each of these categories, how much of this is absorbed by greenhouse gases. Each one of these is a greenhouse gas. Water vapor even is a greenhouse gas. So this is telling you what percentage of these are reabsorbed by greenhouse gases versus if we didn't have as many greenhouse gases, more of these would escape back into space. Therefore, we wouldn't be as warming as quickly as we are. And here is a basic schematic of that. You have the incoming solar radiation. It hits the Earth. during the day. At night, it's supposed to kind of reflect back out or move back out into space, and we're supposed to lose a certain percentage of that. So I'm just going to keep it really simple here. So let's say in that happy medium where our planet has been for a lot of our modern existence as humans, let's say that, I don't know, maybe 60% of that radiation goes back out into space. I'm just making that number up. But let's say with more greenhouse gas, only 30% is able to escape back in space. That means a 30% difference of that heat that usually leaves that atmosphere is staying in that atmosphere. So it's warming it up over time. So again, this is exaggerated. The actual depth of our atmosphere is actually a lot closer to the surface than this. This is just for a visual. Here are some of those diagrams that I mentioned earlier about how our orbit around the sun is kind of elliptical. So sometimes we're further away than others. If we're here or here, we're closer. Out here, we're further away. The tilting axis and spinning axis. So if all three of these line up just perfectly, where we're the furthest away from the sun and have the sharpest tilt of the axis, then it could affect the temperature and make it drop a little bit, basically. A little bit enough to cool the planet to where it could be considered an ice age. But normally, we're not in that kind of cycle. And we're certainly not right now. And this is kind of bringing those all together. This is just an example of what I just described. And as you can see, it has an ice age here, and it has them all lined up in a certain way. So again, here's the orbit. If you've got the axis is tilted here, you're closest to the sun. So this would be the southern hemisphere having a very warm summer and a very warm winter for us as well on the northern hemisphere, because we're closer to the sun, so we're going to get a little bit more of that radiation. But if we're on this part of the orbit, it's going to be a bit cooler. So all these things work together. That's the main point of all this. All these things are working together to contribute to the temperature of our planet. And these greenhouse gases that we're putting into the atmosphere is overriding some of these natural processes. When we expect to see the temperature drop a little bit, it's not. So that's a very, very prominent thing that we use these graphs for. So albedo is another idea. I showed you in that last diagram how the sun directly shines on the Earth's surface. And when it hits the Earth's surface, a lot of it could be deflected. For instance, on the polar ice caps, on glaciers, the snow is typically, and ice is usually white, okay? So when it hits on the white surface, 85% of that heat and light can be reflected back up into the atmosphere. So in normal conditions, it would actually escape the atmosphere. A lot of it would, not all of it, but a lot of it would. And only 15% is absorbed into the water or land or whatever's there. But when it's ice, most of that is reflected. So you look at oceans, 93% is absorbed and only 7% is reflected. So that's pretty low. And on land, it's similar. 90% is absorbed, 10% is reflected. So as you can see, when not ice melts on these glaciers and toward the poles on the ice caps, more surface water or land is going to be a darker color. It's going to absorb more of that heat and light. And as that heat is absorbed, it's going to warm this up. And less is reflected, and it's just, again, it multiplies itself. The more ice disappears, the warmer it gets. The more ice disappears, it absorbs more sunlight, therefore it gets warmer. This is the carbon cycle. Again, this has a lot to do with the amount of CO2 in our atmosphere. I'm not going to go into this in detail. It's in your textbook for time purposes. This is a modern atmospheric CO2 record. So we've actually measured this during these years from about probably 1958 or 59 up through 2020. And you can see it's a steep incline. It zigzags just a little bit year to year just because winter and summer CO2 or carbon is sequestered in plants and animals more during warm months, of course, in the northern hemisphere, especially because we have more land. The trees are actively glowing in the summertime, so you're going to get more carbon tied up in the trees and vegetation. And in the wintertime, it's going to dip a lot more. But basically, if you draw a line through this every year, it's going pretty much straight up. Another thing that we have to think about is it's called the thermohaline circulation. These are basically the ocean currents that flow around our world. These are very important to the climate that we have on our continents. It's also very important to the temperatures that we have in these ocean areas and the weather patterns on all the continents. So what you have here is you have warmer, shallower ocean currents that flow in the red, and then sometimes they transition when they're blue, they're deeper and they're colder. So I'll give you a good example. If you've ever been to Florida or in the Caribbean, you know you've got this warm current coming up across the northern end of South America into the Caribbean, up the east coast of the United States. So those waters are pretty warm in the ocean, right? If you've ever been to California and gone to the beach, even if it's hot outside, the water's always cold in the ocean. That's because they have a deeper, colder current that flows along the west coast. So that's also what drives our weather patterns in the United States. In these latitudes, the weather moves from west to east. So weather systems will form over these cold ocean currents and move across the United States. Same thing with the warm ones in the Gulf of Mexico. Here in Kentucky, we get some weather, especially in the summertime, coming up from the Gulf, and we get moisture from the Gulf, especially maybe think about a hurricane that comes up and hits Texas. We're going to get a lot of rain from that a lot of times in Kentucky, depending on how that's steered by the upper level winds. So these are very important. If you look at, for instance, England and Ireland. So here's Europe, right? In my geography class, I teach about the latitudes and the climate of Europe. So if you look at Kentucky right here, sometimes we don't really understand where Europe is in comparison to the United States. It has a similar climate, so we think it's about the same latitude. But if you look at Kentucky, we're further south than any European country. All of Europe is more north than much of the United States. It's up in the Canadian latitudes. So you would expect it to be a lot colder. However, because this Gulf Stream goes across the Atlantic and it's relatively warm water that flows from toward the equator over to here, you have England and Ireland that are islands in the ocean that are pretty far north. Look at where it would be in Canada over here. It would be up in the Hudson Bay area, which is really cold. But because of this stream right here, they get a lot of precipitation, moderate weather. It never gets really, really cold there. It doesn't get really, really hot there, but it stays pretty moderate. They get quite a bit of rainfall. But the whole continent, the western part of the continent, stays pretty moderate and similar to the climate we have here in Kentucky, even though it's further north. That's what kind of impacts that these currents can have on even continents. So these are driven by salinity in the water and temperature in the water. So if these currents start to break down, we're going to have big problems in world weather patterns. And as the water right now is getting more acidic all the time, and more fresh water is being melted up here in the northern latitudes, the ocean is getting less salty, more acidic, and it's having an effect on these ocean currents. They're starting to get weaker, which is a big, big warning sign for us. If you've ever watched the movie The Day After Tomorrow, I'm not sure when it was put out, maybe late 90s or early 2000s. That's a catastrophic type of movie where the climate changes in like 3 weeks. It's probably a little fast as far as how quickly it changed, but it's based on those ocean currents kind of going dormant and causing big upheavals in the climate of the planet. And that kind of reminds me of a meme I see a lot online and social media, that every catastrophic movie about natural catastrophes begins with a scientist being ignored in the beginning. And that's, I kind of relate to that because it's probably pretty true that politicians and economists don't always listen to the scientists. El Nino and La Nina, this is a weather phenomenon that is over the Atlantic Ocean. It has to do with the warmth of the water around the equatorial areas. It has a big effect, even though it's a long way away, on our weather. I'm not going to get into a lot of detail on it. You can look this up in your textbook, but it has to do with the temperature of the surface of the ocean waters. When we do these models, this graph is just for you to understand that when we are monitoring these things, I say we, I mean climatologists, when they're looking at weather patterns and climate models and wind circulation models, it's a 3D proposition. It's not just surface winds blowing one direction. They're looking at every cubic space of air going up the atmospheric column and which way these winds are blowing, if they're rising, if they're falling, so vertically and horizontally. It's a very complicated modeling process that is done on these things. It's not just something simple that we're kind of assuming things. This has been studied in extraordinary detail. So this is a pretty telling graph as well, these two put together. So the green line in both of these is the same. And this is the observed temperature over these time periods, okay? So you'll hear a lot of people say this is a natural process. And there are things that affect these natural processes, like volcanic eruptions sometimes, if they're big enough, can affect the chemicals in the air. That's true. If you look at these graphs, you see after these big volcanic eruptions, you see a drop in temperature actually each time. Over here you see the orange line is a model. So we put this in the computer, okay? And we put this in the computer, and over here we're putting in both the pollution that people, anthropogenic, it's kind of a mouthful, but that's human injected and natural types of events in our atmosphere. Over here is just the natural events, just the volcanoes and whatever happens in nature. And the green line is the actual temperature that we've recorded, okay? The orange line represents what the computer models tell us happening with the pollution and with the natural disasters like a volcano. And as you can see, the model is pretty accurate within the green line here with the pollution. However, if you took pollution out of the equation and you only monitored the natural inputs of these chemicals in the air, the model says the temperature should be here. And it's actually up here. So that right there, that model is telling you how much human influence there is on the climate, the current climate and global warming. So what happens now? So again, this textbook was published about 3 years ago, so this is about 3 years behind. But for all intents and purposes, we're close to the same point. So if we didn't do anything, if we just kept doing what we're doing, the line would be here. And the global temperature would rise. And this is Celsius, so this is a little more than Fahrenheit. So it would rise. If we actually reduce emissions right now, these chemicals are still going to stay the same in the atmosphere because, like I've said several times during this semester, it takes a while for these things to kind of remediate themselves. In other words, if human beings disappeared from this planet tomorrow, if we all went away and there were no more cars driven, no more coal burned, anything else, those chemicals are not going to go away out of the atmosphere overnight. It's going to take years and years for the planet to start to heal itself. So if we disappeared tomorrow, or we didn't put out any more emissions that we are right now, we're going to keep this line going like this. But if we keep doing what we're doing and not change anything, we're going straight up into a danger zone up here. So again, going back to what I mentioned earlier, there are ways that we kind of can study paleoclimates through sediment, tree rings, glacial ice. All those things are ways that scientists can determine what the environment was like. Glacial ice is typically the most reliable and most accurate because you're basically getting an air sample from the ice of what it was. It's frozen in time. So you're getting a really good snapshot of what that is, and that can go back thousands of years. A tree ring, the lifespan of a tree can be a few hundred years, so that's useful for more recent years. Sometimes you might find trees preserved in bogs or anaerobic environments, and so you can go back further than that. But the glacial ice is really where it's at as far as what we can see in those ice samples. And they take core drills, they just drill down, and they have a whole profile of ice that can span up to, a few thousand years. And they can look in this ice and they can determine what was in the air at that time, what the temperature was. So this is from the glacial ice. You can see thousands and thousands up to 400,000 years ago. And you can see the direct correlation between global temperature and carbon dioxide in the air. And every time it goes up, temperature goes up. Now, this is the previous glacial period that we had, and you can see for some reason the carbon dioxide tanked right here. So what was that? What caused that? Well, we're probably getting ready to find out in the next few hundred years, I would guess. The scientists have a good idea. However, if you look at this next graph, this is very telling. So this graph down here is going to be your temperature over time. So this is thousands of years before present. So here's right now. This goes back to 50,000 years. This was a glacial period right here. So this was a cold period. And then it started to warm. And then this is most of documented human history through here. And then we get to the end, and although it actually looks like it's cooled off a little bit, this appears a close-up to this. And the reason it looks like it's cooled just a little bit is because we're not really projecting out. We've actually been steadily going up for the last, this is aged thousands of years before present. So if you look right here, we're going up for the last 200 years easily. But we call this the little ice age. So what happens in here? Why did it go down a little bit here? Well, you had events like, let me go to the next slide. You had events back in these days. We had several documented volcanic eruptions. So you say, okay, well, what's that mean? Well, there's a couple things that happens there. One is in the earlier years of the industrial age, we didn't burn quite as many hydrocarbons as we do now. And a lot of our pollution in the earlier industrial age was particulate matter. Now we don't have much particulate matter. That's also the primary pollution from volcanoes is particulate matter. So you're saying, okay, well, what in the world is particulate matter? Particulate matter is actually tiny specks of dust. So think about it as dust or tiny specks of sand that gets injected to the atmosphere. And they're light enough that they stay aloft in the upper level winds sometimes for years and years. What they do is they block out the sun. So basically, after a big volcanic eruption, you should expect to see a drop in temperature if it's big enough. Now, small eruptions, they're not going to touch it. But back then, they had some very big eruptions, and they were enough to cool the atmosphere. And that typically lasts at least a couple of years after a big volcanic eruption. Add to that, in the early days of the Industrial Revolution, most of that pollution is particulate matter. So it tends to work to block out the sun rather than to create greenhouse gas. Now, there was greenhouse gases being produced by industry. Don't think I'm saying it wasn't. It was. But there was also a whole lot of particulate matter that balanced that out and maybe make it a little bit cooler. But as we started to modernize, we had a little up and down here. And then basically since the 1970s, we've been going straight up. And that has to do, too, remember, the population of the world back in these days was not near what it is now either. So that's something else that you had going on back then. So there's so many different factors you have to look at when you start to look at what was going on in the world all around. Not just with one thing or another, but everything together. And with the population in the world today, this is going to continue to go up and up unless we take some drastic measures to overcome this. So again, these are charts just showing the carbon dioxide, the methane in the atmosphere, and you can see here kind of up and down for 800,000, 700,000, going back thousands and thousands of years, and all of a sudden, look at where we are now. This has spiked all the way up here in 2019. Carbon dioxide has spiked straight up. Never in the history that we have been able to document has it gone up this fast, this concentrated, and this fast. You see there's a lot of ups and downs, but nothing that spikes up to here like we have now. So this is truly an unprecedented time in our history. So what's going to happen when the global warming or the climate changes? That's a good question. We've got these models that we've been going to for years and years, and it's actually changing faster than a lot of the models that have indicated it would. So those are being tweaked all the time. The more data we gather, the more accurate the models are going to be. However, since this has never happened like this fast, it's hard to have an accurate model because most models are based on previous events and previous data. So we're kind of in uncharted territory here. And the short answer to that is we really are not sure what all's going to happen. We know some things that will happen. We know sea level will definitely rise significantly. There have been times in our past that during the dinosaur age, for instance, there were probably no polar ice caps at that time. They were all melted. Sea level was unquestionably higher, but we don't really have a good record of that because it was so long ago. But we certainly have seen records where we can extrapolate that sea level has been much higher than it is now, and it will probably be so again in the coming decades or centuries, whichever come. I don't know how fast it's going to happen, but it's probably going to happen. So we're going to change our weather. We're getting more extreme weather. I've seen this over my lifetime. Again, I've discussed this in previous lectures about how even in my lifetime, I've seen much more extreme events, and we see it every year. And that doesn't just mean stuff that happens when it's hot. You know, you see some of these yahoos every year that say, well, it snowed a lot in Texas, so that must mean global warming is not No, that has nothing to do with it, trust me. That's actually extreme weather. That means there's some balance off somewhere that's causing that to happen. These polar vortexes that we hear about in the winter that makes it really cold here, that's not normal for us to get a lot of those. That means somewhere else in the northern hemisphere, it is so warm that it's flowing up to the North Pole and pushing that cold weather down where it shouldn't be. That's what that means. So actually, that is an indication of climate change, but not what those people would like for it to believe, for it to happen. So another unknown is precipitation patterns. So overall, the theory is the warmer the air is, the more moisture it can hold, the more humid it can be. So you might think, well, we're going to get more precipitation. Well, yeah, there's a lot of places that will. And in recent years, Kentucky here, we've been getting more. We have. However, if a complete breakdown occurs of our climate system, then we could just as easily become a desert in the next few decades. I mean, we just don't know right now because we're in uncharted waters. We're not sure. If those precipitation patterns break down, things could happen very quickly. The West is getting drier and drier. The Midwest out in the Great Plains is getting drier and drier. That's been documented during a severe drought out west. Probably you've seen on the news about the lakes drying up. There's some of the rivers drying up. It's getting really bad out there. We're going to have more glaciers melting, and the permafrost is going to melt, leading to, again, that methane escaping and making it more hot. Another thing we have to think about, too, is in a lot of countries, for instance, my wife is from Peru, and on the west coast of Peru, it's desert. The only way they have a lot of population on that west coast, where all the population is rivers flowing from the Andes down to the ocean from glaciers. If all of those glaciers melt in those mountains, there will be no source of water on the west coast unless they get it from the ocean by desalination, which is very expensive, as we learned previously. So a lot of people in mountainous areas depend on melting ice and glacial deposits for their drinking water and their source of water. If that goes away, then the population is going to have to move at an unprecedented scale to different areas. Here is just a kind of an overview of the weather patterns and how the winds move. This is very general in nature. but it kind of shows where we are, temperate and humid, temperate and arid in the subtropical zones. Typically around the equator it's humid and warm. So this area is actually expanding north and south, and we're not sure how all this is going to change in the future. We do know this is expanding into the polar areas. The temperate and the humid is getting larger, and the polar areas are getting smaller, certainly. This is a map by USDA. This is currently, I don't see a date on here, I don't think. So this is pretty much for probably not 2018. The likelihood of some places getting drier and becoming more desert. And you can see the western United States and even much of the Great Plains here, that's a high probability. From yellow to orange is higher probability. So you're looking at less rainfall in these areas all around the world. The Sahara Desert expanding more southward, and even a little arm over close to Kentucky, the Jackson Purchase area, it's showing could be a lot drier in the future. So again, these pictures are from 2014 of some of these lakes. This is in California. It's drier than this right now in California. They've had a tremendous drought out there. Lake Mead out there is the lowest level it's been in years and years and years. They're seeing stuff that they've never seen before because it's never been this low. So they're desperate for water out there, and it's only probably going to get worse. There's no signs of this letting up anytime soon. Again, another picture of a glacier. This is from 1940, and now, same time of the year, 2013, it's receded all the way up into the mountain, and you now have water and green grass growing. So tremendous changes across the landscape of the planet. And this is just a graph of sea level change. Here we are today. It hasn't been at this level for about 120,000 years, and this is going to continue to go up as the climate gets warmer. Some of the reasons that some of those models might not have been so accurate on the amount of ice that's going to melt and how quickly it's going to melt has solely to do with the models really just didn't understand how the glaciers would melt. Not only are they melting from the top, but water's getting down underneath them, and they're melting from the bottom as well. So they're actually melting faster than the models predicted that they would. It's gotten warm enough in these areas that that's allowed to happen. Originally, the models would think it would only melt more on the surface, and the water wouldn't be warm enough. It would freeze before it got back down to the bottom. Or sometimes, say in Antarctica, for instance, this ice sheet might be out over the ocean out here, and this ocean water is just a lot warmer than they predicted it would be by this time. And this is what I'm talking about. You have ice sheets, the ice shelves that go out. So the white is land, and the blue is the ice shelves. And these are what are melting faster than they predicted that they would. Some of these ice shelves have already started to fail. They've had some pretty big failures down there, and they're predicting more in the future. And pictures, satellite pictures from 1980 of the North Pole versus 2018. Same time of the year, much, much less ice up there at the North Pole. And that's affecting ecosystems as well. When you see the polar bears, some of the seals, they depend on this ice for their livelihood, for hunting and all that stuff. We're seeing big problems with the environment up there and how it's traditionally been. Again, the acidification of the ocean. You can see how much CO2 is in the atmosphere. We saw this graph earlier. Well, the green graph is the amount of CO2 in the oceans. Of course, as you'd expect, it's steadily increasing, and as it gets more carbon dioxide, it gets more acidic. So the acidity, the pH actually is more acidic as it goes down. So it's getting more acidic over time. And here we see, this is a graph again of the CO2 emissions. We know this has been a straight line going straight up, and it doesn't look like it's going to change anytime soon. This graph over here, the pink is the percentage of overall CO2 that's put out by each country. So you can see we're second to China. However, the white is the amount of CO2 put out per capita. That means per person. So China has so many people, they're putting out more than we are, but per person it's really not as much. If you look, we're putting out a lot per person. If you go out here, you see like Saudi Arabia and Canada, both of those countries total are not putting out a lot, but per person they put out a lot because they don't have hardly any people living there. So that's lifestyle. And that tells you where the problem lies in our world with regards to the countries. So how do we fix this? Well, that's not a very optimistic thing to talk about. Conservation, that means don't use as much fossil fuel, increase the efficiency of cars, or go to another fuel source like electric. Pay people to not use it, which has not been done very much because nobody wants to spend money. And then again, decarbonization of energy use. That means go to renewable energies, which we're trying to do, but we have to make it profitable. This is just a graph showing where we are basically, or where we were 3 years ago, and this is what happens if we do these things. If we reduce emissions, we're in the green. If we keep them the same, we're probably not very well off, but it's better than nothing. If we keep going the same track we are, you can see where the CO2 emissions are going if we keep doing this. One way that we can try to help, and I say that kind of skeptically because we can actually set up big filters to filter the air and take CO2 out of the air, and we call that carbon sequestration. Capture and storage means the same thing. And those scrubbers, they basically take the CO2 out of the air, they pump it down to, again, like a deep oil injection, a saline aquifer way down deep that we won't have to deal with in generations to come, and put the carbon down there, and it's out of the atmosphere and out of the carbon cycle. So what's wrong with this? Well, again, all the things that we've talked about before, but you would literally have to have hundreds and hundreds of thousands of these things to even make a small dent in what we're doing right now. So that's economically really out of the question. We cannot touch what we're putting out into the atmosphere right now. And a couple of those videos that I assigned to you guys in our lesson, they have really good examples on it, just how much we're putting out every year into the world. It's stunning how much that we put out on a daily basis. So this is really not an option. We actually deal in carbon credits and carbon storage with farmers some. Certain crops that they grow will take up more carbon from the air and put it into the ground. We talk about things like that, but really these things are very, very minimal. One of the best things we could do is reforest the planet, the Amazon, quit cutting it down. That's a tremendous carbon store right there, and those plants, we're cutting it down at a ridiculous rate right now, and all that carbon also is going to the atmosphere. The more trees we have on this planet, the more plants we have, the more they'll take up that carbon and put into their life cycle. And that's it for this lecture. So that's the last one of the semester. I will be putting this test up in the coming days, and I will have some guidance for you on the final exam as well. So be looking for that, and good luck to everybody at the end of the semester.